Okay, this tutorial will be covering when to use the combined gas law and when to use the ideal gas law. So first as a background, we'll be deriving the ideal gas law from the individual gas law. So both of these, this is important to realize that both of these are derived from three gas laws. You could derive it from Charles' law, which states that if you have a volume and you multiply the temperature by some constant that we'll call B, then the two are equal. Okay, another way to state that is the volume is directly proportional to the temperature um, multiplied by some constant. Okay, if we have Boyle's law, then that states that if we multiply the pressure times the volume, then we get some constant that we'll call A. Now I'm gonna rearrange this and solve for volume, so I'll get the following. I'll get V equals um, A times 1 over P. Okay, and then if we have Avogadro's law, this is the volume is proportional, directly proportional to the moles of gas you have. So I'll use K for this constant, K times N here. Now, if I combine all of these, so if I combine all the V's here, okay, then I get the following. So I get the volume is equal to, if I take all of the constants, so this one, and this one, okay, if I take all the constants, then I get B times A times K times, and if I combine all of these terms here, if I combine this, this, and this, then I get T times N over P. Okay, this right here, this happens to be if you multiply these, and these are experimentally determined constants. And if I multiply all of them together, I actually obtain R, the familiar gas constant for R, which is 0.08206. And the take note of the units. It's liters times atmosphere over moles times Kelvin. Those are the units for R. So if I clean this up a bit, then I get V equals R times T times N over P. And if I um, clean this up a little bit more, then and I move the P over, then I get PV equals nRT. Okay, and I get the our familiar ideal gas equation. Okay, and this equation we'll go over when to use it on the in a couple slides from now. Okay, now an interesting thing happens here if I solve for R. Okay, using the ideal gas law, um, we'll derive the combined gas law. Okay, if I solve for R, then I get the following. I get R equals V times P over N times T, or I'll just put P times V. Okay, now if I have a new set of conditions, let's say I have the same gas, okay, and it's at a pressure of one, I have initial pressure, initial volume, initial moles, initial temperature. Okay, if I change some variable, like if I raise the volume, okay, then I will have a new set of conditions. But if I look at this equation, they should still equal R. So R will also equal a new set of conditions, which I'll use a subscript 2. So P2 times V2 over N2 times T2. Okay, so this is the same gas but under new conditions here. Okay, so I like to say this is before and this is after. Like say you have a balloon, okay, and this balloon is at like 0 Celsius, so it's extremely cold. And then let's say you take it indoors, okay, at like 22 Celsius. Okay, what will happen to the volume? Okay, should get bigger. Okay, and you could use this is what I mean by before and after. Okay, and so if you set these, since they both equal R, you could actually set them equal to each other, and you'll get the following. You go P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay, and then this is the combined gas law, and we use this for before and after reactions. Okay, so a couple more things on when to use the combined gas law. So I've never actually sat and memorized like all the different gas like Charles law and Boyle's law. So I always just kind of stick with this one here, and then I'll read the problem and figure out which variables are being held constant. So that's what we're going to do on these couple of slides. So here's the combined gas law. So now when P and N are constant, then this is an example is a tied leak-proof balloon, okay, dipped into liquid nitrogen, for example. Okay, then you'll get the following. So if P is what I mean by P being fixed is that's just if you have a flexible container. So this would be like having a balloon. Okay, then and if we tie it, that means N is also fixed. So no moles of gas can come in this balloon and nothing can get out of this balloon. So N is fixed and the volume is allowed to expand. So that's why we need a flexible container and but pressure will actually stay constant. So there's pressure exerting by Earth's atmosphere and then there's pressure this on the inside pressing out on this balloon. Okay, and now when if you heat it up, it's allowed to change the volume without changing pressure because you have a flexible container. So what ends up happening in this situation here is the pressure and moles cancel out because they're the same before and after. So P1 will be equal to P2 and N1 will be equal to N2. So if you were to take this balloon and then dip it in liquid nitrogen. Okay, so what happens if you have volume and N are constant? Then that would mean you have a rigid container, so volume would be fixed, okay, and this container is sealed. So an example would be an aerosol can thrown into a fire. The two variables that would be affected are pressure and temperature in that case. So if we look at our ideal gas law, the volume and moles cancel out of this equation because you have a rigid container. So V1 will be V equal to V2 and it's sealed. So N1 will be equal to N2 because moles of gas cannot get out. So an example or a device that actually illustrates this is this pressure gauge. Okay, that has so here we have a gauge. Okay, and it's reading some amount of pressure. Okay, and then there's this steel ball here, and right here is a valve, and N ends up being fixed because air cannot come out of here and air cannot get in. It's closed by this valve here. Okay, and then this is a steel rigid container which occupies the gas that's being measured. Okay, so if you subject this to like a cold temperature, then the molecules in here will move a lot slower, and the gauge, the pressure gauge, would go down. Whereas if you expose this to a really high temperature, then the molecules will be going crazy in here. Okay, and then it will make the pressure rise. So this is how you study P and T: is you isolate N and you isolate V by making a rigid container. So that's you'll see problems that do this also. Okay, where like and here's an example. So a can being thrown into a fire. Okay, so that would be like a hairspray can. Okay, so volume is fixed, and there's a valve here, so N is also fixed. Okay, so the two variables at play here are P and T. Okay, so let's move on. There's one other situation that can happen. Okay, and that's if you have T and N held constant. Okay, and a device that does that would be like a syringe. Okay, so if you have or if you move a gas to a larger container. Okay, so this would be one way to fix um, the uh, the temperature. So a situation where you have this could be if you have a syringe. Okay, and this is and you have a cap here, so N is fixed, and you just keep it at the same temperature, and this allows the temperature to stay constant from before and after as well. So what we're doing here is we're allowing the volume to change, and we're allowing the pressure to change by keeping moles fixed. So if we depress this plunger, as long as there's a cap here, the moles of gas will stay the same. Okay, so gas cannot come in and gas cannot get out of this hole because it's capped. And if we keep it at the same temperature, then that's the easy way to fix temperature as well. So this device here, if there's markings here to measure volume, a syringe will allow us to change the pressure and it will allow us to change the volume. Oops. So it'll allow us to change the volume as well. Okay, so that situation will become this is actually Boyle's law. So you could see all three gas laws, actually including a Gay-Lussac's law. So you could actually see all the gas laws just by looking at the combined gas law. So if we go back one, okay, this one here is actually um, Gay-Lussac's law, which is the study of pressure and temperature when N and V are constant. And this top one here, this one is, if you notice, is Charles' law. Okay, and you could actually there's ways where you could study Avogadro's law as well by isolating pressure and temperature. So there's ways to do that as well. Okay, so let's go ahead and look at a actually before we look at a problem, let's summarize this here um, with the two gas laws. So when to use which gas law? When you notice two or more variables are changing, okay, these I like to refer to these as before and after problems. Then we're going to use the combined gas law. Okay, if the gas is not changing, it's just saying here's a gas. Like let's say you have a sample of O2. Um, oh, before we move to that, all temperatures, important note here, when you use the combined gas law, all temperatures have to be in Kelvin. Okay, and this prevents us from having negative temperatures here if we were to use like Celsius or Fahrenheit, and that would prevent us having from like calculating negative pressures or negative volumes for answers, which is actually physically impossible. Okay, so if you notice the gas is not changing, for example, if you have O2, okay, and it's at 1 atm, okay, and it's at 19 degrees Celsius, and you have like 1 mole of it. Okay, there is no before and after here. It's just here's a gas, here's what pressure it's at, here's how much of it you have, and here's what temperature it's at. Tell us what volume it is. Okay, if you have a problem like that, then we use PV equals nRT. Okay, if you have a problem where you have like the example I used earlier, you have a balloon and the volume is 1 liter and it's at 0 Celsius. Okay, and then this balloon is moved. This same balloon Okay, then this same balloon is moved to 22 degrees Celsius. What is the new volume? Okay, in this case, variables are changing. We changed the temperature, so you have more than one variable changing here. Okay, and then it asks like, what's the new volume? Um, One important note. So back to the ideal gas law. Before you use this one, make sure it can get tricky because moles of the gas, it might be in terms of density, it might be kind of like hidden, so you might have to do side work. So there's often side work to do, including stoichiometry. If you have a problem where you're supposed to use the ideal gas law, like you have this solid, okay, like there's like if you have a solid and then it reacts and gases form, okay, then there might be stoichiometry work to do, okay, including stoichiometry before you obtain the moles here. So moles can be hidden as density. It could be in terms of molarity or molality, this other way to use it. Okay, or it could be in the ratio if it's a chemical reaction. Okay, so this is all background. We haven't done any examples yet. So, and that's what we'll be kind of taking care of in class, is we'll be going over some examples. So as a lesson check, so I'm gonna move to the next slide here, and I'm gonna have you guys try to solve this problem. So as the title implies, we're gonna be using the combined gas law in this problem, and you'll see that multiple variables are changing. So you have a mass of a gas. Okay, and then you're asked to calculate how much gas remains. So moles of gas is changing. The the pressure is changing. So it was this, now it's this. Okay, the temperature has changed. So it was this, and now it's this. So this is definitely a before and after problem. Okay, so work this out and let's see what you come up with. That's the end of our tutorial.